By the time you're watching this, we should be just after the first midterm, which means you've now had a lot of chances on assignments and midterms and in live sessions and things to see how the simplex method can be used to solve linear programs, and to see that it's sort of convenient. We turn our LP into a dictionary, we perform a set of pivots. The pivots are a bit tedious, but we don't seem to need that many of them. And then it tells us whether the LP is unbounded or whether it has an optimal solution. And of course, we also know that if the initial dictionary is not feasible, we have a procedure for either finding a feasible dictionary or deciding that there is no feasible dictionary and that the LP itself is infeasible. But we sort of have one huge question that we have to answer still, which is, does the algorithm actually work? So just because I can turn a problem into a dictionary and I can perform some pivots and I end up with an optimal solution doesn't mean that I have an algorithm to solve any linear program. Maybe we've just been lucky. Or maybe it's true that the simplex algorithm works on any LP of, let's say, 3 variables or 4 variables, but it fails catastrophically if I add any more than 4 variables. So we still have to answer this question. We have to investigate what it would mean for the simplex algorithm to actually be an LP solver, to be able to solve, or at least give us an answer for any LP. And the answer could be infeasible, unbounded, or it has an optimal solution, here it is. So we have to address that, and we really haven't done so far. We have a few hints of maybe what it definitely is doing right and what it could do wrong. So one example, which I'll come back to in a few minutes more in more detail, is that we know that if the simplex method reaches that terminal dictionary, if it reaches a dictionary where every objective coefficient is negative, then we actually do have a lot of reasons to believe that that is indeed an optimal solution, if it reaches that point. We also know that all the LPs we seem to try do eventually reach a point like that, or we find that things are unbounded. So it's one thing to say, if it reaches that point, it's found an optimal solution, but how do we know we'll always reach one of those terminal points where we can tell that it's unbounded, or we can tell there's an optimal solution? So basically all we've really seen so far is that, yeah, on all of the examples we try, the simplex method can figure out whether the problem is infeasible or feasible. So if it's infeasible, that initial dictionary is infeasible, and we try to solve an auxiliary problem. If the auxiliary problem can be solved with that parameter omega going to 0, then the LP is feasible. We can get our feasible dictionary. We can then run the simplex method on the original LP to decide whether it's unbounded or to find an optimal solution. This has worked on the examples we've tried, but that's far from being able to say that the simplex method always solves an LP. We have to show that it always reaches one of these outcomes no matter what you throw at it. No matter what linear program you throw in, it'll always reach either the outcome that the problem was infeasible, the outcome that the problem is unbounded, or the outcome that there is an optimal solution. Now, actually, what we really have to demonstrate is simply that the method eventually terminates, because we've defined that the only 3 conditions under which we will terminate the iterative process are deciding the LP is infeasible, deciding it's unbounded, or deciding that it's optimal. So actually, all we really have to do, if we've defined those as the only end conditions, is to prove that it always reaches one of those end conditions after some amount of time. And that is something we're going to do between this lecture and the next one. And what we'll come down to is having to more clearly define some of the choices the algorithm makes and consider the consequences of those choices. Before that, I want to address this. This is a nice appetizer problem, especially coming back from a midterm or something. This example isn't directly relevant to what I mostly want to talk about in the next couple of lectures. It's something that we do have to address, though. We could have addressed this at the end of the previous lecture or something, but it will also give us a taste of a certain property of the algorithm that we are going to need to talk about a lot today. So here's an LP. It is unusual, according to the slide. The only way it's unusual is the strange appearance of the objective function, for 2 reasons. One, we generally try to avoid objective functions with constants sitting in them like this. And 2, this objective function not only has a constant, it doesn't have anything else. None of the optimization variables participate in any way in this objective function. So it's unusual. The first thing, some of you might have the gut reaction, this seems sort of like cheating. It doesn't look like a real LP. But it is. It's reasonable for me to ask bizarre questions like, can you maximize a constant function? Because what I'm really asking here is there any feasible point subject to these constraints? I mean, we know that the maximum is going to be 1 if a maximum exists. We also know, I think it's obvious, that this is not going to be an unbounded LP. I mean, clearly there's no way to make this objective function go to infinity. But there's still that other possibility. The LP only has a maximum if it has feasible points. So what this is really doing is it's actually just, it is a linear program, but really what it's doing is asking the question, is there any assignment x1, x2, x3 that meets all three constraints? So we can set up a dictionary for it, and we get this. Notice that, of course, the objective row is empty, but that zeta value initially is just set to the constant 1, which is the constant from the objective function. And notice that the initial dictionary is, in fact, feasible, which means if I set x1 to be 0, x2 to be 0, and x3 to be 0, I get a feasible point. And you can look at the original LP, and you can see, well, clearly, the right-hand side of each of these less than or equal to constraints is positive, which means if I just set everything on the left to 0, the constraints will be satisfied. So it shouldn't surprise us that the all 0 vector is in fact feasible, which actually means this is an optimal dictionary, because there aren't any positive coefficients, so I can't pivot, and therefore I'm done. Okay, great. So I've managed to solve this strangely vacuous objective function, this LP with the vacuous objective function, without doing any work. Okay, well maybe that was making the problem too easy. So the all 0 vector is an optimal solution for this LP. In fact, any feasible point is an optimal solution for this LP. But that doesn't necessarily mean the LP is completely trivial, because for there to be a maximum, there has to be at least one feasible point. And we can elaborate a bit on this by making the LP a little bit more complicated. I guess in the meantime, the slide wants us to answer this question, which is, sure, this is a very strange looking dictionary, but what are the non-basic variables? And this is just to head off, in case you were thinking, oh, well, there isn't anything up in the objective function. Aren't the non-basic variables the things that show up here? Well, no, the non-basic variables are every variable that isn't a basic variable. And it's obvious that regardless of the behavior of the objective function, these are our basic variables. So everything else is non-basic. So x1 is non-basic, x2 is non-basic, and so is x3. It's odd that they don't show up in the objective row, but the reason they actually don't show up is because I haven't written them in. They are there, because I could write them as 0x1 plus 0x2. We just try to avoid writing out the zeros because it makes the screen more cluttered. So they are still non-basic variables, even if they're not participating in the objective function directly. And the slides are pointing that out. Any variable not in the basis is a non-basic variable. So let's take a look at this. Here's a modified version of the same LP, which isn't initially feasible. And again, if you have an LP in standard form, you can look just at the LP itself to decide if it's going to be initially feasible, if it's in standard form, because if the less than or equal to constraints have a negative number on the right-hand side, we know that the all 0 assignment is not going to satisfy the constraint, so it won't be initially feasible. So this LP is still, it has this very trivial objective function, but the initial dictionary isn't feasible. And I want to make the point that just because the objective function is trivial doesn't mean you don't have to do any work to solve the LP. So we construct that initial dictionary, it isn't feasible, what do we do? Well, we do the same thing we would do in any other case, which is we try and find a feasible dictionary and then run the simplex method from there. So we're going to need to set up an auxiliary problem using our parameter omega and then solve the auxiliary problem. I will show all the steps to that again so that this can become a nice practice exercise if you need review of the simplex method later. So I need to set up an auxiliary problem. So I do that. So this is the dictionary for the auxiliary problem. We know, of course, as usual, the initial dictionary for the auxiliary problem isn't feasible. But we know as well that we can perform one strategic pivot to make it feasible. And remember, just like from the last lecture, that the pivot that we perform to make the auxiliary problem feasible isn't really part of the simplex method. Because in the simplex method, we only do pivots on variables. The entering variable has to have a positive coefficient in the objective function, and this one doesn't. But this is a strategic pivot to make the dictionary feasible. So we do that, we end up with this. And of course, it is a feasible dictionary. Notice that, and this is a good primer for the rest of this lecture, that the objective function value was 0, but the dictionary was infeasible. I performed this strategic pivot, something that the simplex method would never do, to make the dictionary feasible. In so doing, I get a feasible dictionary, but the objective function value goes down. That's how I know this would never be a pivot performed by the simplex method. Because in the simplex method, the only pivots we ever perform are those that would not decrease the objective function. And you can try and parse what I just said. I didn't say that a pivot has to increase the objective function. All I'm willing to say is that the pivots that the simplex method normally does can't decrease the objective function. That's how we know the pivot we just did is a special pivot that isn't really something the simplex method would normally do. So that's one thing. What an odd way of phrasing that, Bill. The other thing I might want to point out is, after I do this pivot, I end up with a basic variable that's equal to 0. Which is maybe a little bit creepy. Now, we're used to variables equaling 0. We know that our non-basic variables are defined to always be set to 0 if we interpret the dictionary as we do when we're running the simplex method. We also are aware that if I want to know the value of a basic variable, I just read it off of the constant column. But then I notice that I've got this basic variable that's set to 0 as well. So can I do that? And for now, the way we're going to try to address that question is just see whether it breaks anything. Let's just keep trying to run the simplex method and just hold on tight and trust it and see whether anything goes wrong. And we'll notice that in fact it doesn't. So I'm solving my auxiliary problem. I choose x2 as my entering variable. If I examine the ratios that I get, so I have my entering variable x2, and the ratios that are imposed here are 2x2 is less than or equal to 4, 2x2 is less than or equal to 1, and here, okay, that's odd. So, well, we know how to compute these ratios. I end up with 0 minus x2 has to be greater than or equal to 0, which is really saying that x2 is let's see, less than or equal to 0. It's putting an upper bound of 0 on x2. I realize I should probably expand these out. So this is saying x2 is less than or equal to 2, and this is saying that x2 is less than or equal to 1/2. And we'll notice that this basic variable that got set to 0, because it is a possible leaving variable relative to the entering variable x2, it automatically becomes the leaving variable because it imposes a very tight upper bound on x2. x2 has to be non-negative, and here the upper bound is 0. So of course w3 has to be the leaving variable. So that 0 is already causing me a bit of grief, but it seems like I can still do the pivot, and so I do. Notice that after the pivot, the variable that entered, so x2, ends up also equaling 0. Now, this shouldn't surprise us too much. It's still a little bit creepy, but it shouldn't surprise us too much because if I think about what I do once I've selected w3 as my leaving variable, I have to solve this constraint for x2, and so I get x2 equals 0 minus x1 minus w3. There's my problem with writing w's again. w3 plus 2x3 minus w1. And so we know that because of the way we have to solve these equations, it shouldn't surprise us if we pivot with our leaving variable set to 0, we're going to end up with our entering variable set to 0 on the next iteration, and it is. Okay, so let's just hope that nothing went horribly wrong there. So at the next step, I pivot using x3 as my entering variable, and we'll notice that x2, which is that 0-valued basic variable, we don't need to consider it as a leaving variable because of the positive coefficient. Okay, so fortunately we can ignore that 0 for now. So we choose w2 as the leaving variable, and we perform another pivot, and we end up here. Notice that x2, which was 0, is now set to something else. The result of that last pivot I did increase the value of x2, so it's no longer equal to 0. Although I've got a bunch of fractions over 5 here, this dictionary does look a lot more comfortable than the one we just saw. This is something that is a sort of typical looking simplex dictionary. We perform another pivot and another one after that, and now we end up with this optimal auxiliary dictionary. We have the optimal objective value is set to 0, and that tells us that we can, and omega is non-basic, which means it's going to be equal to 0. It means that there is a feasible solution to my original LP with omega set to 0, which means I can transform this into a feasible dictionary for my original LP. So go back to the previous lecture to see how we did that. That's something you probably have to do on the midterm as well, so hopefully you know about that by now. I'm going to skip over all of that algebra. We convert the dictionary, so here's the feasible dictionary for the original problem that I get by deleting omega and reintroducing the original objective function. I should add that the step of reintroducing the objective function would normally require subbing in some variables. Fortunately for us, our objective function is dead easy. We just throw in the constant 1. So we get this. And then we stare at the result. This is my feasible dictionary for the original LP. And I notice that because my original objective function was a constant, so my original objective function was f of x1, x2, x3 equals 1. And we know already, if you think back to the lecture on LP geometry, so the gradient of f is going to be the all zeros vector. So f is a constant function. And we know that the gradient of f will be 0 everywhere in my feasible region, which means any feasible solution is an optimal solution. Which of course means as soon as I have a feasible dictionary for my original LP, I'm done. It's already an optimal solution. And remember that it's true there could be lots and lots of different, distinct optimal solutions, but if you ask me to maximize a function and I find you an optimal solution, that is the answer. I don't have to provide any specific optimal solution. If you wanted a particular solution, you should have given a different objective function. So it's the usual problem of if you asked me to maximize a function and I find you a maximum, and you wanted a different maximum, you didn't ask the right question. So maybe you don't always want what you want. So this is optimal, the objective value is 1, fair enough. And any other feasible dictionary that I could contrive would also be optimal for this problem. So that begs the question, how do we construct another solution? So to be clear, if you're writing a simplex solver, this is the answer. You're done. You found the optimal solution. You can give an optimal assignment of variables. But suppose you were asked, modify your solver to generate more optimal solutions. We know there might be more than one of them. Could you generate some more of them? And the answer is, well, yes. So we can do any pivot that we could perform that doesn't change the objective value, keeping in mind that if you're at the maximum, the only pivots you can perform that do change the objective value and stay feasible will decrease it. If there are any pivots you can perform that don't change the objective value, they will take you to another distinct optimal solution. And one thing we can observe is if we pretend that every non-basic variable is in the objective function with a coefficient of 0, which is true, really, we can then perform these pivots. We could say, let's choose an entering variable. So for example, I could try and use x2 as my entering variable. It does have a non-negative coefficient. It's a 0 coefficient, which means no matter how much I increase x2, the objective function value won't change. But that's the point. If I want to construct another optimal solution, I don't want to change the objective value. So I could perform a pivot using x2 as my entering variable and then choosing the leaving variable by the usual logic. So because no pivot can change the objective value, any pivot that I can perform that still keeps me feasible will give me a different optimal solution. So for example, I could pivot with x2 leaving and x2 entering and x3 leaving. And that brings me to this. And notice that I get a different dictionary, obviously. I performed a pivot. The objective function is still the same, and I end up with a distinct optimal solution. So equally optimal, but a distinct assignment to variables. And of course, any feasible solution is optimal. Now, one thing I should observe is that the only solutions you're ever going to get out of a dictionary like this are vertices of the polytope. If my polytope, I'm not saying it does, but suppose my polytope looked like, I don't know, this quadrilateral here, then every vertex is an optimal solution, but of course so is everything in the interior and everything on an edge. If you want to generate all optimal solutions and you keep pivoting this dictionary, all you're ever going to see are all the vertices, because the dictionary, when you pivot it, just takes you between different vertices of the polytope. If you wanted all of the solutions, let's say along this edge or in the middle, what you could do is generate all the vertices using pivoting, and then you could construct all the different convex combinations of the vertices. That would get you every possible point. Now, obviously, I don't know why you want to generate that infinite number of points. If you wanted to specify all possible points somehow, that's how you would do it. Get all the vertices and then specify convex combinations of those. And I should also observe that we tend to have it is distinct, like to talk about an optimal solution that lies along an edge or inside the feasible region versus one that occurs at a vertex. And because we know that an optimal solution will always occur at some vertex, we tend not to care too much about the difference in terms of solving things, but it's important to know that there is a special name for that. So what we are looking at here, any dictionary that is feasible defines what is called a basic feasible solution to the LP, which is unfortunately, for me, somebody with a graph theory background, often abbreviated BFS. So I don't like that at all. BFS means something else to me. And a basic feasible solution corresponds to some dictionary where if you have n optimization variables and m constraints, a basic feasible solution will have n non-basic variables and m basic variables, and it will be feasible, hence the word feasible, and it will actually correspond to a vertex of the polytope. And the simplex method, when you pivot, is moving between different basic basic feasible solutions to your LP. But there could be other feasible solutions like interior points, and there could be other optimal solutions. So a basic optimal solution would be a feasible dictionary. So n non-basic variables, m basic variables. A feasible dictionary that happens to also be optimal is a basic optimal solution. But there could be other optimal solutions. And if you want to construct them for some reason, the simplex method won't necessarily do that for you. So then the question is, I was able to construct two optimal solutions to this LP. And the question we should think about as a thought question is one better than the other? And the answer, of course, is no. If you ask me to maximize this objective function, anything I give you that realizes that maximum is equally good as anything else that realizes that maximum. If you had a preference, if you think one solution's better than another, you should have given me a different objective function so that I could have somehow differentiated between the different solutions. And that's the key point. I've brought that up repeatedly in other lectures and in live sessions and things, that often if you look at the solution to an optimization problem, whether it be linear or anything else, and you say, this isn't the solution I wanted, well, then you probably weren't asking the right question. Now, it's interesting, this is something that will come back up in a few weeks. It actually turns out that any linear program, regardless of how complicated the objective function is, any linear program can be rewritten in a form by adding extra constraints and extra variables, such that the solutions are all the same, but the objective function is trivial. So if you give me a linear program with a non-trivial objective function, I can transform it into one that is with a trivial objective function where the solutions are all the same. In other words, it turns out that really the difficulty of solving any linear program does seem to lie in figuring out whether any point is feasible, because you can convert any linear program into that question. Is this feasible or not? Give me any feasible point. We'll come back to that later. That's a result that comes out of a subject called duality, which is very important to us, but we're not going to get to it for a couple more weeks. Let's talk about something else. In fact, I think one aspect of that previous example that we really should explore a little bit more is what happens if a basic variable goes to 0. And that is something called degeneracy. And this example will show that off. So here's an LP that is, as far as we can tell, pretty unremarkable. It's in standard form. There's not even any, all the coefficients are equal to 1 or 0. It's initially feasible because there's no negative signs over here. So it doesn't seem as if there's anything overtly threatening about this LP. And we'll construct our initial dictionary. Still looking good. Everything looks good over here. I will also declare that it has a bounded feasible region. So there's no reason why going to infinity should bother us for this LP. Not that it should really bother us in general either. So let's try solving it. So we try pivoting. And as usual, we'll use our largest coefficient rule to determine the entering variable. And we know that in the event that there are multiple candidates that are tied to be the entering variable, we have to come up with some resolution scheme. And generally the one I've been using in the other examples and things is we'll just choose the lowest numbered one. If we have multiple variables that all have the largest coefficient, choose the lowest numbered one. Same for leaving variables. So we'll choose x1 as our entering variable, and then we've got two choices for leaving variable, and they're tied. They both give the same ratio, so we'll just choose w1, the lowest numbered one. Okay, so we pivot, and then we end up here. We end up with a basic variable equal to 0. So the same situation we had before. And we noticed before it was weird, it looked creepy, but everything still worked out. We just, soldiered on, and eventually that 0 disappeared and everything was fine. So what happens when you end up with a basic variable that equals 0 is we end up with what's called a degenerate dictionary, and we call this a degenerate basic variable. And the reason we use the word degenerate there is that I guess we've been following this convention that we obviously expect a lot of variables to equal 0. So the non-basic variables are supposed to be 0. But that's where we're supposed to be putting our 0-valued variables. We expect the 0-valued variables to be the non-basic ones. So to have a 0-valued variable end up in the basis is sort of a special case, so a degenerate case. And we call the whole dictionary degenerate in that situation. Now, what happens next depends on a lot of different factors, including things like which pivot you select. So a degenerate dictionary is not inherently invalid. It's completely fine for a degenerate dictionary to exist. And it is a valid step in many runs of the simplex algorithm, both on this slide and in practice. And we'll notice it is still feasible. The only thing we're not allowed to do is set our variables to be negative, because we know that every variable has to be non-negative. But 0 isn't negative, so we're good. The problem is that these degenerate basic variables can provoke some strange behavior. And in some cases, if we're very unlucky, they can result in behavior that breaks the simplex method. So let's just hope that everything's going to be all right and keep moving. So we'll notice that at our next step, if we want to just keep pivoting, we have to choose x3 as our entering variable. We have to. So one argument that sometimes people want to make is, well, a degenerate pivot, having to pivot with our degenerate variable being the leaving variable, that results in some weird behavior. And we're going to see some more of that behavior in a few minutes. Maybe if we choose our pivots differently, we can avoid ever having to do such a thing. But notice that here there's only one choice for entering a variable, and it's x3. If I go compute my ratios, then this imposes the bound x3 is less than or equal to 0, and this one imposes the bound x3 is less than or equal to 2. So there is only one choice of leaving variable, and it's w2. I have to tackle this head on. I have to pivot with my degenerate basic variable. So I do. X3 is the next entering variable, and I now have to pivot with W2 because that implies X3 is less than or equal to 0. What this is saying is I chose X3 because I wanted to increase the objective function. I mean, that was the reason I chose something with a positive coefficient, with the logic that if I increase the value of X3 to some non-zero value, the objective function value gets bigger. But then I discover, oh, wait a minute, X3 can't be any bigger than 0. So I have to keep x3 at 0. I can still do the pivot, but x3 will not end up with a positive value. It'll end up stuck at 0, which means the objective value can't change either. So I do the pivot. We call this a degenerate pivot because we'll see the variable x3 ends up still having the value 0 when we're done, and the objective function value doesn't change. But on the other hand, we could do the pivot. Nothing seems to have broken as a result, although it is a bit unsettling that our objective function value didn't increase, because the whole point that we used to derive the simplex algorithm to begin with was choose your entering variable to increase the objective function. So that's something to worry about, but it seems like everything's still working. So let's just see if I can push on through. So in this case, I choose x2 to be my entering variable. Okay, thanks, slide. Fair enough. So I choose x2 to be my entering variable, and I choose w3 to be my leaving variable. And notice how here, I again have this degenerate dictionary with a degenerate basic variable x3, but because the coefficient is positive, it's not considered as a candidate for the leaving variable. So the pivot I end up doing doesn't involve x3. So I pivot x2 and w3, and I end up with this. And notice that because of the substitution I had to do when I did my pivot here, x3, which was previously equal to 0, now equals 1, and even better, the objective function, which was equal to 2, is now equal to 3. So I'm back on track. I was able to raise the objective function again after that. So I also end up, fortunately, at an optimal dictionary. So everything's negative up here, so in fact, I'm actually at the optimal solution. So here we saw that degenerate dictionaries can exist, and they are, to a large part, harmless. If they show up, we can end up in this strange, unsettling situation where the objective function value doesn't change, but for whatever reason, if we rearrange the dictionary a bit, we can often find ourselves a pivot that we can perform that does increase the objective function value, and it gets us moving again. So degenerate dictionaries aren't necessarily inherently problematic. However, this idea that we can perform pivots that don't increase the objective function, that is troubling. Because we consider that up until this point, if the objective function is increasing at each step, we know that we're never going to repeat ourselves. Because if I'm sitting at this dictionary, let's look at one of the earlier dictionaries here, like this one. If I'm at this dictionary here where the objective function value is 0, and I'm guaranteed that if I perform pivots, the objective function will be some larger value, then I'm also guaranteed I will never end up back at this step again. There's no way I can repeat myself if the objective function always has to go up, because it'll never go back down again. If there are steps where the objective function stays the same, I'm opening myself up to the possibility that maybe I could take a series of steps with the objective function never changing and end up back where I started. And that's a big problem. And I think maybe when the slides were being melodramatic a minute ago, that's what the slides might have been referring to. So there's this fact. We're going to get to this fact again at the end because it is a fact, but we haven't seen all of the reasons why it has to be true. So the fact is, if every pivot is guaranteed to increase the objective value, then the algorithm is guaranteed to terminate. It is guaranteed to eventually reach that optimal dictionary, because if you have to keep adding a positive value to your objective function at each step, eventually you're going to get to the maximum value. There are some nuances to this fact that I'm going to come back to at the end of the lecture, though. We now know, however, that this fact, that the if condition here isn't always satisfied. The fact says if every pivot increases the objective value, then the algorithm will terminate, guaranteed. But we've seen that there are cases where some pivots don't increase the objective value, and that could be a problem. Before I talk about the obvious, before I show the problem, I want to talk about a geometric thing. So here is a linear program, and it has this feasible region. Now notice that it isn't initially feasible. So here's 0, 0, which is obviously not in the feasible region. This linear program has 5 constraints. So there are these the 3 obvious constraints, but there's also these 2. So there are 5 constraints. And notice that the feasible polytope has 3 sides. So this, this, and this. And it turns out that each of the 3 sides corresponds to one of these things. The other 2 constraints are that x is greater than 0, that's this, and y is greater than 0. And I mean, we take these constraints for granted, but they are real constraints. Okay, we also know that if I have a linear program with n optimization variables, so a linear program in n dimensions, so this is one in 2 dimensions, if I have a linear program in n dimensions, I should expect that a vertex of my polytope occurs at the intersection of n different constraints. So this, for example, this vertex here occurs at the intersection of these 2 constraints. So 2-dimensional, 2 constraints at each vertex. And so I should expect, if I look at each vertex, there will definitely be 2 constraints that are met at equality at that vertex. And similarly, at the other constraints, there are in fact 2 constraints met at equality here. But there aren't only 2. It turns out that there are 3 constraints being met at equality at this point. There are at least 2, but it's not necessary that there be only 2. So the 3 constraints are this one, and that was a bad parallel line, this constraint, and the constraint y is greater than or equal to 0. In a sense, that means that this vertex down here is sort of overspecified. It's the intersection of more than 2 constraints. You only need 2 constraints to define a vertex in 2 dimensions, and yet there are 3 constraints intersecting here. And the reason for that basically is that these 2 constraints, x is greater than 0 and y is greater than 0, they don't really contribute to forming the feasible region. They're extraneous. If I deleted them, which I can't because of standard form, if I deleted them, the feasible region would be exactly the same. But they do graze the feasible region at these points, and so they do occasionally get factored in when I consider which constraints are met at equality. So let's keep that in mind. Remember that the LP wasn't initially feasible. I omitted the part where I solved the auxiliary problem, but this is the feasible dictionary produced by solving the auxiliary problem. And it puts us at this vertex down here. So we have a pivot, we've got an entering variable, so we perform a pivot with y as the entering variable, and we end up here. And remember from before that this is the intersection of, in fact, 3 constraints. So the 3 constraints would be the constraint that x is greater than or equal to 0, and 2 of the other ones. And I suppose that the other ones are probably w1 and w2, because they're both of those 2 variables are set to 0 here. So w1 is set to 0 because it's non-basic. w2 is set to 0 because it's degenerate. And we should consider now, maybe geometrically, why it is that we have this degeneracy problem. So normally we expect that at any feasible step, there will be, in this LP, 2 zero-valued variables, because we know that at any vertex of the polytope, there will be 2 constraints that are met at equality. And we know that when a constraint is met at equality, its variable in the dictionary has to equal 0. So it makes sense that our dictionary is designed so that at every step, there are guaranteed to be 2 variables set to 0. But what happens if you have 3 constraints being met at equality? Well, obviously, you only have 2 slots for non-basic variables. So one of those 3 constraints has to be a basic variable. And that's why we end up with a degenerate basic variable. Because there are cases where more than n constraints intersect when you're working in an n-dimensional LP. And that means that whatever constraints are extra, whatever extraneous constraints are present, they have to be basic. And we can't necessarily even guarantee that the one that ends up being basic is the one that we don't need. So I mentioned that really the constraint x is greater than 0 is the extraneous constraint here. If we deleted that constraint, we'd have the same polytope. So in a sense, x is greater than or equal to 0, it should be the odd one out. But the way this dictionary is configured, unfortunately, W2, which is one of the actual sides of the polytope, it is the degenerate basic variable. So that's just too bad. That's just the result of the arithmetic transformation that I performed to get here. Okay, so the basic feasible solution that I'm currently looking at is the one that I read off from the dictionary. So x is equal to 0, y is 3/2, w1 is 0, w2 is 0, w3 is 3. Okay, fair enough. We know that we can read those off of the dictionary. Let's do another pivot. I have only one choice for entering variable, it's W1. I have only one choice for leaving variable, oh, and it's this thing. It's the degenerate basic variable. So I know that at my next step, my objective value will not increase because W1, my entering variable, is stuck at 0. But I still perform the pivot. Okay, so I perform the pivot. Oh, the slides are now talking about that overspecified thing. Sorry, I guess I got a bit ahead of the slides there. I perform the pivot and I end up here. Let's read off the value of each variable. So x is equal to 0, it's non-basic. So x is 0, y is equal to 3/2. Okay, w1 is 0, w2 is non-basic, so it's 0, and w3 is 3. Well, that looks a bit familiar. If I go back before the pivot, that's exactly where I was. And this shouldn't surprise us too much, because before my pivot, w1 equaled 0, w2 equals 0. When I was done my pivot, w1 equals 0, and w2 equals 0. So I changed nothing. All I did was rearrange my dictionary. I put something in the basis and I took something out, but I stayed in exactly the same place geometrically. So it's tempting to think about these degenerate pivots as sort of walking around where the objective function is equal to one value, but you're not really walking around at all. You're just staying in the same place. You're standing on one vertex of the polytope, sort of shuffling around your files, shuffling around basic versus non-basic. That's it. And hoping that if you rearrange basic and non-basic in the right way, you end up with some pivot that's going to take you out of this rut, that's going to get you back to increasing your objective value. Okay, so I've done this degenerate pivot. I now have a new dictionary, so a distinct dictionary, but for exactly the same feasible solution. I've just rearranged the dictionary. And now I cross my fingers and hope that I can perform some pivot that gets me out of here. In this case, I do. So if I use x as my entering variable, let's clean this up. If I use x as my entering variable and then w3, which is the only choice, as my leaving variable, well, then I can get moving because I know that now I can actually give x a non-zero value, which means in turn that the objective function will increase. And that takes me up here, and it turns out this solution is optimal. Okay, so I can breathe a big sigh of relief. I had this degenerate dictionary. I looked at it geometrically and discovered that if I do these degenerate pivots, I'm literally standing still, which is worrying, and yet I was able to escape. I was able to get to my optimal solution. The problem is that's not always possible. And it's worth considering, I mentioned at the beginning, how do we know that the simplex method isn't just a clever trick for 2- or 3-dimensional LPs? How do we know it's going to work for 1,000 variables or 1,000 constraints? One thing that's interesting, I don't have the exact number off the top of my head, but the book talks about this, is that nobody is aware of an example that demonstrates the worst consequences of degeneracy with any fewer than this number of variables. So literally, when you're working in 3 dimensions, this is not going to be a problem, strangely. This is a linear program that I pulled out of an ancient paper. I think it was from 1955. I really had to dig to actually find a copy of the paper. I'll talk about that in a minute. This is a classic example of what is, I wonder what we're going to call this thing, a really awful consequence of degenerate dictionaries. Something that would not be a problem at all if we could guarantee that a degenerate dictionary would never be encountered. So you can see that it is definitely a very contrived LP because it already has all sorts of weird fractions all over the place, even before I've constructed any dictionaries. So it was constructed purposely to try and elicit this behavior. Okay, so let's try solving this and then cross our fingers and hope nothing goes horribly wrong. So my problem is initially feasible. I've got an objective value of 0. Okay, fair enough. And it's fine if the initial objective value is 0. I'm not alarmed just yet. Of course, I've got x1, x2, x3, x4 non-basic, which is the normal configuration for my initial dictionary. w1, w2, w3 basic. Okay, fair enough. Let's just get cracking and hope everything goes well. So I choose, as my entering variable, I choose x1 because my usual largest coefficient rule dictates that that is the only possible choice. Now, I do have a choice between whether I pivot on w1 or w2, but I guess I'll choose w1 because we'll just choose the lowest numbered one. Although it turns out it actually makes no difference. The problem isn't going to be any easier to solve if I use w2 instead. Okay, so I do a pivot. Great. And then I'll just keep walking. I'll just hope that after enough pivots, this problem gets solved. So there we go. We're pulling in x1 and x2 into my basis, although each of the pivots I've had to do so far has been degenerate, so my objective value is still stuck at 0. But fair enough, I seem to be making some progress, so I keep going. Okay, there we go. Iteration 7. Wow, that's a lot of pivots. Still degenerate. And actually, you know, that looks a little bit alarming. W1, W2, W3 are in the basis, but it looks like something's going on up here. I seem to be making progress. There's x3 and x4, and x1 and x2 are over here, so maybe I'm still making progress. We'll keep going. Okay, there's 8, 9, 10. Okay, so why is this not going up? 11, 12, 13. And then I stare at this for a minute and I say, actually, you know, I'm having some deja vu here. So W1, W2, W3, they're in the basis. Okay. x1, x2, x3, x4, uh-oh. So I've ended up walking around in a circle. I have done a bunch of pivots. I appeared to be getting some work done, and I ended up back at my initial dictionary. So here's my initial dictionary. Sorry if it's too small to see. And here's iteration 13, or just before iteration 13, so 12 dictionaries later. And I ended up exactly where I started. And each of the pivots that I did not change my basic feasible solution. It just shuffled variables between the basis, in and out of the basis. That's it. And so it didn't improve the objective value. And that's why I had to be a bit worried, because if the objective value isn't going up, I run the risk of retracing my steps, ending up where I've already been. And in these 12 dictionaries, that's exactly what happened. But actually, even worse, it turns out I was back where I started at iteration number 7. So I paused at iteration 7 to point this out. At iteration 7, my basis was back to where it was at the beginning. But it did look as if I was making progress because my non-basic variables weren't in the original order. But maybe you can satisfy yourself that the actual ordering of rows and columns is sort of irrelevant. I mean, we can rearrange rows, we can permute rows and columns all we want in our dictionary. And if you look at the coefficients between these things, if we go to the slide that compares them, and I guess you can zoom in if you want. I'm recording this in glorious 1080p, but I have a feeling that UVic's video server isn't displaying it in that resolution. If you were to compare these iteration 1 and iteration 7, you might notice that the coefficients are all exactly the same. The ordering of columns is sort of irrelevant in this case. And so I went around in a circle. In fact, you could argue I went around in a circle twice. And we know if we just let the simplex method run, it's going to go around in an infinite loop. It will never finish. Even worse, it'll never even get close. It'll never be able to break away from the objective value 0. So obviously, this is a huge problem. We'll give it a name. It'll be the obvious name. It is called cycling. So it's a situation where the algorithm gets into an infinite loop, which of course really breaks the algorithm. The algorithm, I mean, the definition of algorithm from day 2 of CSC 225 was it is only an algorithm if it finishes in a finite amount of time. And this is not that. So we're going to have to find a way to fix this. And that'll take us all the way to the end of the next lecture. So degenerate dictionaries happen all the time. We've already seen a lot of them in this lecture. And most of the ones we've seen up to this example were harmless. We got to a degenerate dictionary, maybe we do 1 or 2 degenerate pivots, and then we find an escape route and we keep going. We increase the objective value and everything is good again. And degenerate dictionaries do happen all the time. Cycling is actually very rare. So if you randomly generate an LP, it is improbable that the simplex method will cycle on that LP, using, let's say, the largest coefficient rule to choose a pivot. So it turns out cycling is actually extremely rare. It is, in a sense, sort of an accident. I think one of our books talks about it in those terms, because if you think about it, cycling happens in cases, so if we look at that example we were working with before, where we had a vertex of the polytope where 3 constraints intersect. It's pretty unlikely that you have that situation. You've got n dimensions, but you end up at a point that's the intersection of n plus 1 constraints. That's relatively unlikely, and it's also unlikely that when you get there, you'll end up walking in a circle. You won't find some way to escape. So it's actually very rare for cycling to occur in practice. It's also worth considering that if we think about the way that LPs get solved in practice, there are lots of ways that we can insulate against cycling occurring just sort of by accident. And one of them is that if we use floating point arithmetic for our calculations, instead of this exact rational arithmetic that I insist on, if we use floating point arithmetic, we know that as we keep running these computations, little rounding errors might accumulate. And the rounding errors are enough to throw off my constraints by just a little bit. And if I keep iterating through my system and performing additions and subtractions and multiplications, maybe the rounding errors pile up just enough to throw off my constraints slightly and pull, instead of having all three or n plus 1 intersect at a single point, instead they diverge just enough to avoid degeneracy. That's actually a special case of a formal method called perturbation, or the lexicographic method, that we're not going to cover in this course, but it is one way to resolve cycling. To prevent cycling is to just apply a random perturbation to every constraint so that they don't happen to all line up at the same point. And so as a result, because we use floating point arithmetic a lot in practice, and you will on your programming project, cycling is actually much more unlikely than it would normally be in practice, although we still have to prevent it because it still could theoretically occur. And we especially have to find some way around it if we're going to use the simplex method to verify theoretical results. And of course, if we want to claim that the simplex method can solve LPs, because if we can find an LP that the simplex method can't solve, then it obviously isn't an LP solver. So this slide is actually it's jumping to a conclusion. We shouldn't say that the responsibility lies with the pivot selection rule. I guess what I meant to say here was that in the example we just went through, the pivot selection rule was the reason why we ended up cycling. If we had chosen a different pivot selection rule, we might have been able to avoid cycling. There are lots of different pivot selection rules. We'll talk about a few in the next lecture. And it's true that this LP cycles under the largest coefficient rule, which is the one we've been using up until this point. I could choose other pivot selection rules and this LP wouldn't cycle. But all of the other performance-oriented rules that exist seem to have LPs that cause cycling. So although I can avoid cycling on this LP with a different rule, I can't avoid cycling altogether with necessarily any particular pivot selection rule, especially the ones that are performance-oriented. So what I mean by that is, if you think about why we use the largest coefficient rule, the reason is because we think, okay, so suppose this is my dictionary and not the LP itself. I could choose either of these as my entering variable. But I choose this one because the coefficient is larger on the grounds that maybe I get more mileage out of it. If I can increase x1 to have the value 5, the objective function will increase more than if I can increase x3 to have the value 5. So the largest coefficient rule is sort of performance-oriented. I want to get the objective function as high as I possibly can at each step. There are other rules that are more nuanced than that, but they're also performance-oriented. They choose their entering variable based on some measurement of how much it increases the objective function. All of the performance-oriented rules that are actually used seem to be susceptible to cycling. There are LPs we can construct that produce cycling with those pivot rules. There are pivot rules that prevent cycling, but they're not performance-oriented. So under those rules, they may not cycle, but the method might take a much longer path to the optimal solution. A huge number of extra pivots might be needed because they don't choose the entering variable based on what will actually increase the objective function the most. And we'll talk about one of those rules in the next lecture. Now, there are also ways to modify the algorithm to avoid cycling. And I think when I said that the responsibility lies with the pivot selection rule, what I meant was using the construction of the algorithm that we're using, where we choose an entering variable, choose a leaving variable, and pivot, and we don't do any other magic to the LP beforehand or afterwards. The only real way out, the only place in the algorithm where we make a choice is the pivot selection rule. And I guess to resolve ties if we have multiple candidates for entering or leaving variables. There are ways to either modify the algorithm or to slightly modify the LP to prevent cycling, and that would apply under any pivot selection rule. But of course, we then have to discuss how to modify the algorithm and prove that that works. Two such modifications are, well, they're sort of the same method in two different framings, but the perturbation method and the lexicographic method. So these are actually sort of the same thing. Both of our books talk about these. You can take a look at them. We're not going to cover them in much detail in this course unless a CSE 545 student does their presentation on it. Because for our purposes right now, my goal is just to get us to a point where we know that the simplex method will never cycle. And the way I'm going to get there is by using a different pivot rule, not by using the lexicographic method. So there's a citation here. This LP that I used to demonstrate is from this paper. I believe this is one of the classic examples of cycling with this pivot selection rule, one of the original examples of that. And it was a pretty old paper, and I had to figure out how to get a copy of the Naval Research Logistics Quarterly. I eventually was able to find one at some, I think like U of A or something had a copy. There's also an example which when I made these slides, I wasn't as fond of the example in the Vanderbay book. I think it's about equally as elegant now that I've actually made the slides, but I chose the example I did because now you have two different examples of LPs that cycle. There's the one on the slides here and the one in the book. So now a few other theoretical results, and then in the next lecture we'll talk about pivot rules in general and also how to choose a pivot rule that does not cycle. So the first thing is, and this is a theorem I'm going to elaborate on in the next few slides, if the simplex method does not cycle, then it must terminate in a finite number of steps. So in other words, if I can guarantee that at each step the objective function increases, certainly that prevents cycling, then it will terminate in a finite number of steps. This is just saying if it does not cycle, though. So the objective function can remain the same during certain steps as long as I guarantee I'll never repeat a dictionary. If that happens, then it will terminate in a finite number of steps. To demonstrate that fact, I have to establish 2 points. So one of them is that I need to show that there are only a finite number of different vertices I could possibly visit. So that's a key point. And I can do that in 2 ways. I can show that there are a finite number of vertices of the polytope using linear algebra, which wouldn't actually be that high level, but maybe some of us don't have the same background that others do. Given what we already know in this course, we can also just talk about dictionaries a bit. So one observation that we ought to make is that if I give you a set of basic variables, if I say x1 is basic, w1 is basic, and w2 is basic, and that means that, let's say, x2 is non-basic and x3 is non-basic. If I tell you what your basic and non-basic variables are, everything else is dictated by the system of equations. So if I tell you I want x1, w1, w2 to be basic, here is an LP, you can then construct the dictionary formed by that set of basic and non-basic variables, and it's going to be the same one every time. So there's no other variables in play besides which variables are basic, which things are non-basic. And so we can actually count how many possible different dictionaries are there. Well, all we do is choose which variables are basic and which ones are non-basic. So if I have, I guess I should have left that up there. If I have m basic variables and n non-basic ones, the number of different dictionaries that I can form is just the number of different ways I can choose my basis. So that's n plus m, choose m. Or alternatively, n plus m, choose n's. I choose either the basic or the non-basic variables. So this is the number of distinct basic feasible solutions. Or at most, because it could be some of them are degenerate. They correspond to the same basic feasible solution. But this is the number of different dictionaries that I could possibly construct up to the ordering of rows and columns. Because it's true that, yes, I could reorder x2 and x3 here and get what appears to be a different dictionary. If I consider that in this number, all that would do is multiply this number by n factorial, or m factorial. So I could account for all possible rearrangements of rows and columns by multiplying this number by n factorial, m factorial, which obviously those are going to be big numbers, but they are finite numbers. And so what this is proving is there are a finite number of different dictionaries that can be encountered during the simplex method. It's large, but it is finite. And this is saying if the simplex method does not cycle, well, if the simplex method does not cycle, then logically it can only visit each of the different possible dictionaries at most once. I mean, if it went back to the same dictionary it's already visited, that would be cycling. So if it does not cycle, and there are only a finite number of dictionaries it could ever visit, then clearly it will eventually hit the optimal solution. I mean, it could have to check every single dictionary, but unless it's allowed to loop back and check one again, which it isn't because it can't cycle, it will eventually hit the optimal solution. So there's that. So because there are at most this number of basic feasible solutions, at most, because keep in mind, this is counting the number of different dictionaries. Some of those dictionaries could correspond to the same basic feasible solution, and some of them could be infeasible dictionaries. But in the worst case, there are at most this number of different basic feasible solutions. And so either the simplex algorithm will cycle, or it will terminate after at most this number of steps. So we have that, but then there's still the question, okay, so will it cycle or not? Like, how do we demonstrate that it won't cycle? And there are two avenues we could take. First, theorem A says, if we can prove that no degenerate dictionaries will ever be visited, so this is actually we could also prove that there are no degenerate dictionaries, but this is a bit of a weaker statement. If I can prove that via some modification of my algorithm or my LP, that no degenerate dictionaries will ever be visited, then the simplex method will never cycle. Okay, so we know that the method that we've been using can give us degenerate dictionaries. Suppose we could find a way to guarantee that there were no degenerate dictionaries when the simplex method was running. If that's the case, it will never cycle. So there's one way to prevent cycling. And the proof of that is pretty simple. So if there are no degenerate dictionaries, then at every pivoting step, the objective value must increase. The only time the objective value stays the same is if I have a degenerate pivot. And there are no degenerate dictionaries under the assumption of the theorem. Since there are only a finite number of possible dictionaries, and each dictionary's objective value is a property of the dictionary, it's a constant, then each pivoting step reduces the number of other dictionaries I could possibly ever see. Because obviously if I visit a dictionary with objective value 3 and I do a pivot to take me to objective value 5, any other dictionary with objective value 3 will never be seen again. They're all ruled out. So every time I visit a new, I increase my objective value, I eliminate a bunch of other dictionaries from my search space. And that means eventually I'm going to get to a dictionary, I'm going to reach either an optimal dictionary or find that the problem is unbounded. I'll just run out of other options. There's a footnote here, which is, it's interesting to observe that if all I can demonstrate is that the objective value always increases, without knowing the theorem I just proved a minute ago about the number of dictionaries, if all I can say is that I guarantee the objective value to increase, that actually doesn't guarantee that the algorithm will finish. Because unless I've proven that there are only a finite number of different dictionaries, I guess I could still possibly have this problem of, suppose my initial objective value is 0 and the maximum is 1. And my first pivot takes me to 1/2. And my second pivot takes me to 3/4. And actually, I'm going to redo the example. Sorry. My first pivot takes me to, that'll work. Okay, 1/2, 3/4. And then it just takes me closer and closer. So 7/8. 15/16. And so each pivot is increasing the objective value, but unless I can prove that there aren't an infinite number of vertices on the polytope, this could theoretically just keep converging closer and closer to 1 without ever actually hitting it. There could be an infinite number of vertices, and I'm just hitting each vertex and asymptotically approaching 1. And if you consider the fact that there are optimization problems, so for example, nonlinear optimization problems where you do have this problem, this is one reason why it's nice that we're working in a linear setting, because we can prove things about the number of vertices of the polytope, or equivalently, the number of different dictionaries. Because there are only a finite number of dictionaries, there is no way I'm going to end up asymptotically approaching my maximum value over an infinite sequence of dictionaries. That obviously can't happen. Okay, so that's one option. One option is if I can find a way to modify the algorithm or the LP such that there is never going to be a degenerate dictionary, that will fix the issue. That will prevent cycling. But that might be a lot of work. I might have to, redevelop my algorithm. Now, there are ways of doing that. I mentioned a couple of them earlier. The books talk about it. The way that I'm going to pursue is theorem B. So the second option is if I choose a pivot selection rule that prevents cycling, then obviously the simplex method won't cycle. And if that happens, that's actually sufficient to say that it will solve any linear program, either by finding an optimal solution or deciding that we've fallen into one of these other two cases, unbounded or infeasible. Now, of course, that begs the question, well, great, Bill, what pivot selection rule do you suggest? So we'll talk about that in the next lecture. But for now, I want to finish off by saying that we have two paths we could have followed here. One, modify the algorithm to prevent degeneracy, or two, make it so that if a degenerate dictionary does occur, we modify the only real choice we have in the current algorithm, which is what is our entering or leaving variable. We modify that selection process to somehow allow us to escape from our cycle. And it's worth considering that if we go back to one of our earlier examples, like the geometric one, where we were standing at this vertex, and we arrived at the vertex from this edge here, and then we made a degenerate pivot and just ended up back at the same vertex. But after enough pivots happened, we found ourselves an escape route. We were able to increase the objective value. It turns out, even in the earlier example where we saw cycling occur, there was a point during the cycle, I guess I can go back and we can look at the cycle again. There was a point somewhere around here where we had a choice of pivot that would have allowed us to escape. I'll see if I can track it down. So here's iteration, at the beginning of iteration 1, we have, let's see, I choose x1 as my entering variable. And I notice that, because that's my pivot rule, it requires x1 to be the entering variable. Both of the choices for leaving variable are degenerate, which means I will not increase my objective value. Suppose I used a different pivot selection rule. Well, here's one. I could just choose x3 as the pivot. Okay, if I choose x3 as a pivot, neither of these two things are going to be the leaving variable because of the positive coefficient. But this will. So w3 will be the leaving variable. Notice that w3 imposes this bound here. That means that if I pivot on x3 with w3, that's non-degenerate. I will escape from the cycle at iteration 1. So if my pivot selection rule were designed so that it would catch this case, then I can escape from the cycle. Now, you might be looking at that and saying, well, then why didn't you just check? When you were computing your entering variable, why didn't you decide whether you had an option of entering variable that was non-degenerate? And in this case, that would have fixed the problem. I could have just elaborated my pivot selection rule to, before it actually does the pivot, evaluate if any pivots are non-degenerate. That would work in this case. But we've seen in earlier cases, and there are other dictionaries that probably have this problem. This is one. So this dictionary here, I have only one choice of entering variable. And notice that it therefore requires a degenerate pivot. So it isn't as simple as just saying, oh, modify the pivot selection rule to only choose non-degenerate pivots, because there are steps where a degenerate pivot is the only pivot available. So we do still need some way to there are ways of escaping from a cycle, but not necessarily from every possible place inside the cycle. And we don't just need a rule that will allow us to escape, we need a rule that we can prove will allow us to escape. It's not sufficient to say, oh, there's a way to escape from that particular cycle. We need to be able to prove theoretically that under all circumstances, whatever rule we end up choosing will always prevent cycling. And we're going to do that in the next lecture.